start today, does anybody have any questions for me? Yeah.
When is time 3 coming out?
Hopefully by the end of the week. Yeah. I think it was about 65%. So
what's the historical average?
A square C. I think C is about the average for the midterm. Yeah.
So was everyone supposed to expected to have the midterm marks back?
Pardon me?
Is everyone expected to have the midterm marks back?
Yes. If you don't, that's because there's something wrong with your Scantron sheet. Send me an email. Okay. All right, so we're back to working on probability, and today I want to show you a couple of things that are maybe surprising results. One of them you've probably seen before, or at least heard about before. It's called the birthday paradox. And the other one is also a really surprising thing. That's called the big box problem. That probably most of you or all of you haven't seen yet. So first of all, the birthday paradox. So the question is the following. If we have a group of n people, then what is the probability that some pair of people have the same birthday? Okay, and this is an informal statement of the question, and we'll formalize it into something that's more mathematical in a second. But just for you guys, if I have, let's say, 23 people in the room, what do you think the probability is that 2 of them have the same birthday? Think it's really small, really unlikely?
Is it like 2 over 365 or something like that?
Well,
365 squared?
not 2 over 365, yeah.
My guess is basically 365. Okay, 365. Okay, 365 times 364 divided by 365 squared. One minus that.
Okay, so that's something like that will show up. But remember, there's n people here. In particular, n is 23 in the question I just asked. So let me ask a simplified version of that. Do you think that that probability is more than a half or less than a half?
Less than
half.
Less than a half? More. So it's slightly more than a half, as we will soon see. So by the time you get 23 people into a room, you have a better than 50% chance that 2 of those people have the same birthday. That's kind of a surprising result, because what we've sort of seen so far to tackle those kinds of questions was the pigeonhole principle. And for the pigeonhole principle to work, you need 366 people in a room to guarantee that 2 of them have the same birthday. Right? Because if there's only 365 days in a year, let's ignore leap years for now, then as soon as you have more than 365 people, then you know that at least 2 of them have the same birthday. Okay, so let's formalize this. We will assume for simplicity that there are D is equal to 365 days in a year. So that's just because of these annoying leap years. So let's not worry about those. And we're going to assume something less that a statistician wouldn't be impressed with. We'll assume any person is equally likely to be born on any given day of the year. Okay, this assumption here, from a statistical point of view, is very iffy. In fact, it's almost surely incorrect because there tends to be a higher birth rate usually 9 months after public holidays, things like that, celebrations. So there's a lot of September is a high birth rate month because September is the 9th month of the year, and everybody had time to make babies around Christmas time the previous year. So this is iffy from a statistical point of view, but for a lot of problems that are not exactly birthday problems, this is a reasonable thing, and we'll see those problems, some of those types of problems shortly, but let's just take it as given for now. All right, so we now can set this up as a probability question. So we have a set of, we're running a big experiment here, which is we take n people, and we ask each one of them, what day of the year were you born on? And they tell me I was born on day 1, or I was born on day 17, or I was born on day 363, and so on. So our set of possible outcomes is I asked the first person what day they were born on. And I asked the second person what day they were born on. I asked the third person what day they were born on, all the way up to the nth person. And each one of them gives me an answer that is an integer between 1 and d, or 1 and 365 in this case, and that's for I in 1 to n. Okay? So this is the set of possible outcomes of this experiment, right? When I get n people into a room and ask each one of them their birthday in particular order, I get a list of numbers here. All right. So what is the event that I'm interested in? Well, I'm interested in the event A, which is some pair of people of the same birthday. And I could write that out in the set notation, which is I'm interested in sequences like this where the numbers are not all unique. So where some number appears more than once. Okay. So already that kind of hints us to how we might want to study this because it's difficult to write. It's not super difficult, but it seems a little tricky to write A in this notation here, but we'll see how to get around that in a second. But let's do a simple example, and just so we can parameterize things, let's call this Sn and An so that n is a parameter of the whole thing. And let's just look at, for example, S2. So S2 is just pairs of numbers. And A2, well, what does A2 look like? So A2 is, out of two people, what's the probability that some pair of them, or the event that a pair of them have the same birthday? Well, if there's only two people, then I know which pair it has to be. It has to be the first one and the second one, because there's only one pair, yeah?
When you said sequence where the numbers are not unique, the birthdays are not unique,
Yep.
is like the example of the sequence S2, is S2 one of those sequences?
No, no. So S2 is just, this is the example of if I ask this experiment for 2 people. So I have 2 people in the room. I ask, what's the probability that they have the same birthday?
Right.
Okay.
And the sequence is a subset then of S, or?
No, I mean S itself, the elements of S, of the possible outcomes of this experiment, each one is a sequence of length n. It's just a list of birthdays of length n. Okay. So the event A2 that some pair has the same birthday, well, that looks like this, right? So first person declares that they were born on day 1, January 1st. And then the second person declares that they were born on January 1. And that means they have the same birthday. Or first person says I was born on January 2nd. Second person says they were born on January 2nd. Or third person says they were born on January 3rd. Second person says the same thing. And so on up to they were all born on December 31st. Each one was born on December 31st. Okay? All right. So this is what the situation looks like for n equals 2. This is the set of possible outcomes. So how many possible outcomes are there in this set? Yeah?
365 squared.
365 squared. So d squared in the notation that we're using. So the size of S2 is equal to d squared. And what's the size of this set? Yeah. So size of A2 is equal to D, right? Just 1, 1, 2, 2, 3, 3, 4, 4, and so on. There's only exactly D things here. And this assumption here that any person is equally likely to be born on any given day of the year translates into this uniform probability space, which says that for any outcome in S, the probability of that outcome is equal to 1 over the size of S. And what that means, so that, you know, in this case, each of these 365 squared possible outcomes is equally likely, or d squared possible outcomes is equally likely. And we saw that for uniform probability spaces, that means that for any event A, the probability that that event occurs is just the size of A over the size of S. So now we know how to answer this question for n equals 2, because probability of A2 is the size of A2 over the size of S2, which is D over D squared, or 1 over D. In our case, D is 365, the number of days in a year, so 1 over 365. Now that's not surprising, because there's another way to think about this experiment, which is the first person declares their birthday, and any one of the 365 days of the year, well, then it has probability 1 out of 365 of being the first person's birthday. So that's not surprising. But doing it carefully this way at least lets us know that there's no surprise, because you know, in general, we will see that the final result is surprising. So we have to work carefully and slowly here. Okay. So any questions about this so far? All right. Good. Let's see if we can handle the general case. So we forget about the text version of the problem. We're really working with this idealized version over here, the set Sn, the set An that we're interested in, And it's a uniform probability space measured over Sn. Okay. And so let's write down a couple of things. The size of Sn, we decided that there's d options for the first person's birthday, there's d options for the second person's birthday, there's d options for the third person's birthday, and so on. So how many elements are there in Sn?
365. Because it's birthday. Sorry, 23.
No. How many? So Sn is a list of birthdays. Yeah. D to the n. We have d choices for this birthday, d choices for this birthday, d choices for this birthday, d choices for this birthday. It's the most straightforward application of the product rule that you can possibly have. Okay. So the size of Sn is d to the n. What we would like to know is the size of An, but that looks kind of tricky because An is defined as some pair in there have the same birthday. But maybe there's actually 2 pairs that have the same birthday. That would also count in An. Or maybe there's 3 pairs or 5 pairs or 20 pairs or 100 pairs. Is there some related set that we could figure out the size of more easily? The complement. So let's define Qn as the event no pair of people have the same birthday. Or another way to say that is every birthday is unique. Right? That's exactly the opposite of this, right? Agreed? So if no pair of people have the same birthday, that means every birthday is different in that list. So Qn is the complement of An, which means we know that the size of An, it's the size of the universe minus the size of the complement. And this kind of thing we have tools to deal with. Because what is this Qn? Well, what I've got over here is n people, person 1, person 2, person 3, person 4, person 5, and so on. And over here, I have d birthdays, or d, let's not call them birthdays, days of the year. Now, if I'm an element of Qn, that means this first person has a birthday. Which can be any one of the D days of the year. The second person also has a birthday. How many options are there for that?
64.
Can be any of these days except this one. So this one had D options, but this one only has D minus 1 options. And this one will have D minus 2 options.
Is it D minus n or something?
And all the way down to D minus n plus 1. Okay. Or if you like, easier to see it this way, D minus n minus 1. N minus 1 people have already chosen their birthdays. This last guy can choose anything as long as it's not one of those n minus 1 things. Okay? All right. So now we get the size of Qn. We get it from the product rule. In fact, we've seen many examples like this. What we're looking at is a one-to-one function from people onto birthdays. And some things quickly fall out here. So one of them is that if we have more people than birthdays, then one of these terms is going to be 0, right? So if I have d plus 1 people, then that last person has no choices left. So they have 0 choices, which means there's 0 ways for that to happen. So the size of Q d plus 1 is 0. But in general, it looks like this. First person has d choices. Second person has d minus 1. Third one has a d minus 2, d minus 3, and so on. And that becomes d minus n minus 1. Like that. And these sort of longish products like this that are descending, we have kind of a way to deal with these, and that's the factorial function. So what does this thing look like? Well, it starts out like d factorial, except it's truncated here. It doesn't contain these terms d minus n minus 1, d minus n minus 2, d minus n minus 3, and so on. So this is actually just d factorial over d minus n factorial. And if you look back in the textbook or the notes, your notes, we've seen a formula like this before. It counts the number of one-to-one functions from a set of size what is it, n, onto a set of size d. Okay. All right, so that's the size of Qn. And so now we know everything we need to know, because what's the probability of an? Well, it's equal to the size of an divided by the size of Sn. That's just from being a uniform probability space. What's the size of an? It's the size of Sn minus Qn. What's that? Well, here we have an Sn over Sn. So that's 1 minus the size of Qn over Sn, which is 1 minus, we have d factorial, d minus n factorial, factorial over d 1 minus d factorial, d minus n factorial, and the size of Sn is d to the n. So we have it here. So there's our answer. If I have n people in a room, there are d days in the year, what's the probability that 2 of those people have the same birthday? It's given by this. And, well, now you can plug in the value d equals 365, and the values, well, any value of n that you want. And what you'll find is that for d equals 365 and n equals 22, the answer you get is where are you? 0.476, and if you put in n equals 23, the answer you get is 0.507. Okay? So with 22 people in the room, the probability that 2 of them have the same birthday is slightly less than a half, about 47%. And with 23 people, it's slightly more than a half, about 51%. So that's kind of surprising, right? That's a very small number of people, feels like, given that the number of days in the year is 365. Okay. All right. So a couple of things here. One is, all right, that's great. We managed to work out the exact probability, and we got this formula here. Let me write it down. We'll call this PND is 1 minus d factorial n minus over n minus d factorial d to the n. But it's not really insightful, is it? I mean, even if I put the numbers 365 here, for me, I can't read much about this thing. I can evaluate it, and then I see, wow, that's surprisingly low value of n, where this rises to a half. But is there maybe some way we can beat this thing up a little bit, so we can understand it a bit better?
Is it d minus n, not n minus d?
D minus n, yeah. D minus n. Otherwise, n minus d is typically negative. So this birthday paradox, that name is sort of famous for this thing, but these kinds of problems are more generally referred to balls in bins problems. And here what you have is D bins. So a bin, so it's more of a British word than a North American one, but it's a garbage can, right? It's like a bin, you put your, something that holds stuff, okay? So you have D bins, and you have N balls, and you throw each ball into a random bin. So meaning that you pick one of the D bins uniformly at random and you put the ball in that bin. And this probability that we just computed is the probability that at least one bin contains at least computer science. Super common in things like hashing. So in hash tables, you study balls and bins because that's really what hash tables are. They're you taking data and throwing it into memory locations, and it's can be a problem when you try and throw 2 pieces of data into the same memory location. So they're the bins are memory locations and the balls are pieces of data. It's also a sort of thing that comes up frequently in load balancing sort of applications. You have D computers and a bunch of jobs that are arriving to do these N jobs. And one strategy for that is when a job arrives, you assign it to a random computer. And then you're worried, what's the probability that a computer is stuck doing 2 things at the same time? So that there's lots of applications of these things. And you can ask lots of questions about this setup that aren't just what's the probability that some bin contains 2 balls, but you can ask 3 balls, 4 balls, whatever. Okay, so, but this is the setup, and it's exactly the same as the birthday setup we talked about. And we have this formula for PND written up there. So 1 minus d factorial over d minus n factorial d to the n. All right, so I'd like to get a grip on this formula because it seems like it's useful to understand a little bit better. And for that, we'll approximate it with maybe something that we can recognize. So we'll use one very simple approximation result, which is that 1 minus x is less than or equal to e to the minus x for every real number x. All right, a couple of things here. So this just means 1 over e to the x, right? E, does anybody know what this is? Yeah?
Is it like the exponential, like this?
Yeah, so this is the base of the natural logarithm. It's also called Euler's constant. It's equal to, I won't write a definition in terms of limits because it's not helpful if you haven't seen it. If you have seen it, then you know it. But it's about, I'm going to stop after one digit, but it's an irrational number that goes on and on and on. So it's about 2.7. It's not huge. It's not very close to 1, and it's also not enormous. So this just says that for any real number x, 1 minus x is smaller than 1 over e to the x. Okay? And if you think about what that says, it's not it doesn't look like a very useful approximation, right? If x is bigger than 1, then this number is negative. So on the left side you have a negative number, and over here you have something that's not negative, a positive number. And so that's for sure. A negative number is smaller than a positive number. So it's not very interesting when x is bigger than 1. And similarly, when x gets, let's just only think about positive x's. So, I mean, it doesn't look like a great approximation, but when x gets very close to, 0, what's happening here? Well, 1 minus 0 is 1. And this is then e to the 0, which is 1. So in that case, actually, these two things match up. So anything to the power 0 is 1, and 1 minus 0 is 0. So these two things match. And in fact, this approximation is actually very, very good when x gets really, really small. So these two things, if x is really close to 0, then these two things start to become closer and closer. All right, so we're going to use that. We won't prove it. You can find a proof in a calculus textbook.
Do we use this because probability is always like between 0 and 1?
We use it just because it seems to show up a lot. Things like 1 minus something small seem to show up a lot in probability theory. That's probably because the complement rule is often a useful way to count things, right? Look at our formula here. This is 1 minus something. So that's already there. We're not going to use it directly on this, but we'll use it on something related to this. Okay. So I'd like to get a good handle on this expression, and better to think of the complementary thing, which was d factorial d minus n factorial d to the n. So not with the big minus 1 in front, but this is the thing that I don't understand, right? I understand what a 1 is. I don't understand this formula very well yet. So let's look at this formula. So Q and D. let's write it out longhand. So that was this thing that had a d on top, and then a d minus 1, a d minus 2, a d minus 3, and that went down to d minus n minus 1. Right, so that takes care of this part of the formula. That's the d factorial over d minus n factorial. We still have to write down the d to the n here. So something on the bottom. On the bottom is d to the n, which is d times d times d times d times d. N times. So there's one d for each thing up here. All right? Okay, let's write that down. Do something trivial. D divided by d is 1, so we can forget about that thing. So then what we've got is d minus 1 divided by d. That's this one. So these cancel. Now we've written down these two. And then we've got d minus 2 divided by d. And then we've got d minus 3 divided by d. And that goes all the way down to d minus n minus 1 divided by d. And well, each of these has a d on top and a d on the bottom, so they all look like 1 minus something. In particular, this first one is 1 minus 1 over d. The second one is 1 minus 2 over d, 1 minus 3 over d, and that goes on to 1 minus n minus 1 over d. All right. Now we're seeing something recognizable. 1 minus 1 over d. This is 1 minus, this looks kind of small, right? This is like, for the normal birthday problem, this is 1 over 365. So that's kind of close to 0. So let's use this. So that says this thing is less than or equal to this guy, which is e to the minus 1 over d. And this is 1 minus 2 over 365. So that's also kind of a small number, close to 0. So e to the minus 2 over d, e to the minus 3 over d, and all the way, if there's not many people, even with n equals 23, 23 over 365 is actually still pretty close to 0. So it looks like this is a good approximation for the things we're interested in anyway. So that's to the minus n minus 1 over d. All right. So anybody remember when I take anything to the a and that same times that same thing to the b, what's that equal to?
A plus b.
Yeah. Right, so when you have exponents like this and you multiply with a common base and you multiply, then that's just adding the exponents together. Yeah?
I kind of lost it at the approximation, the jump from 1 minus 1 over d to the e.
Yep. So according to this, 1 minus 1 over d is smaller than e to the minus 1 over d. Right? Just put 1 over d for the value of x here. And that's all we're claiming, is that it's smaller. All right. And now we want to use this thing to tidy this up. And, well, this says that since we have this big product of e to the powers, then we should just add up these exponents here. Let's do that. So that's going to be e all of these are negative. So we have a minus sign. And we have a minus 1 over d, minus 2 over d, minus 3 over d, minus 4 over d. So there'll be a 1 plus 2 plus 3 plus n minus 1. And all of them are divided by d. That's clear? All right. Anybody know offhand what this is? Okay, so most of you don't. So this sum, 1 plus 2 plus 3 plus 4 plus, yeah? Good, you got it. But you're one of a few who seem confident in that answer. So let me tell you a little story about that sum. So this is the famous Gauss story, famous mathematician Gauss, like long German name, Carl Friedrich Wilhelm something.
Wilhelm Gauss.
The story, which may or may not be true, goes like this. Gauss was 9 years old. He was sitting in math class. His teacher was feeling lazy that day, and he told all the kids in the class to add up all the numbers between 1 and 100, all the integers 1 through 100, thinking that the teacher could then sit down and relax while this happened. But before the teacher was done writing the question on the board, Gauss put up his hand with the answer, and it was 50-50, 5,050. So how could he have added up 100 numbers that quickly? Well, he realized there was a trick. So what the question is asking you is, how many squares are there in this picture, right? This is 1, 2, 3, 4, 5. How many squares are there in this picture? Well, you can count the squares. That's one way to do it. But what Gauss noticed is if you take this picture and rotate it 180 degrees, they land here. The 3, they land here, and the 4 land here, and the 5 land there. And this picture is kind of, counting the squares in this picture is kind of easy without counting, because I have 5 rows and 6 columns. So the number of squares in this picture is 5 times 6, right? It's just the area of a rectangle. But I don't want all of the squares, I only want the white ones. But the number of white squares is exactly half the total. So that gives the general thing. And in general, if I have, this number is k, then I get something with k rows and k plus 1 columns. So the answer is k times k plus 1 over 2. So I use that here with k as n minus 1, and I get the answer that you knew immediately, which is e to the minus, this will be n times n minus 1 over 2. And if we squint a little bit and look at this, this kind of looks like e to the minus n squared over 2d. And so where's the place that we're interested in, or where does the interesting stuff kind of happen? Well, around the exponent 1 here, then if this exponent is 1, then this is 1 over e, which is, 1 over 2.7. That's where things kind of get interesting, where the probability is not really small, and it's also not really close to 1. And when is this 1? Well, it's when n is about the square root of 2d. So somewhere around n is around the square root of 2d, that's when things get interesting, when the probability somehow flops between being less than a half and bigger than a half. And that's why 23 people is a reasonable number for 365 days. Another way to interpret that, where's this n squared coming from? Another way to think of it, which we'll maybe revisit when we do expected values, is that the number of pairs of people is about n squared, right? It's n times n minus 1. So, and we already saw that if you just look at two people, the probability that they have the same birthday is 1 out of 365. So it's kind of like you did that experiment, not n times, but n squared times. So it seems reasonable that if n squared is about 365, then it starts to become more and more likely that you get two people with the same birthday. We'll formalize that a bit later, but for now that's a sort of intuition where the n squared is coming from. Okay. So any questions about that?
How do you know that like it's the approximate?
It's people who work in this field. In fact, anybody who's done a reasonable course in calculus kind of learns that actually this is a good approximation for small values of x. And really useful because it works for every value of x, so you don't have to worry if it's true or not, it's just whether it's good or not. So whenever you see 1 minus x and x is small, you can think about, well, maybe it's easier to think about e to the minus x. And same thing, if you see 1 plus x and x is small, then e to the x is also a good approximation. Okay. All right, now for the second surprise, which you've probably never heard of. This is called the big box problem. And it's a game that you play. So here's how the game goes. I pick two numbers. X and y. X is smaller than y. And these numbers, you think of them as dollar amounts. Between $0 and $100. And we're using loonies, so I don't get to do fractional amounts. Okay? So x and y, they're secret, but not necessarily random. So there's just two numbers that I choose. My two favorite numbers between 0 and 100. I take two identical boxes, place X dollars in one and Y dollars in the other. Shuffle the boxes, close them, and show them to you. So far, this is what you see. Two boxes. You know all the rules of this game. You know that I pick two numbers, X and Y, and that I put money, X dollars in one of the boxes, X dollars in two of the boxes. You don't know which one has X dollars in it and which one has Y in it. So this is what you see, But you know that the real picture, if you could see through the boxes, there's only two possible things. X dollars on the left and Y dollars on the right, or Y dollars on the left and X dollars on the right. Okay? This is what you see. You know it's one of these two things, but you don't know which one. You open a box and see some number of dollars inside it, $A, and then you have to decide. Do you keep the box and the money? Or B, take the other box? All right. And W, which stands for win, means you leave with the box containing Y dollars. So you win if you end up leaving with the box that contains more money. All right. So first thing you can see is, well, so the question is, how should you play this game? What's the best way to play this game? And the other sort of meta question is this an interesting game or is it completely boring? So it's kind of obvious that I have a strategy where I can win with probability 1/2, right? And that strategy is open one of the two boxes, or don't even open it, just take one of the two boxes and walk away. Okay. With probability 1/2, you end up with the box that has Y dollars in it. So that's easy to win this game with probability 1/2. Do you have a strategy that guarantees you win with probability bigger than 1/2? Seems difficult because you don't know these values of X and Y, right? So I look in a box and I see some money there. I mean, maybe if I see $100, I know I should keep it, and if I see $0, okay, I should take the other one. But other than that, who knows, right? I mean, if you see $2 in there, then you say, well, maybe I should switch to the other one, but who knows, maybe the other one has $1 in it. So, can you guarantee that you win with probability bigger than 1/2? And it seems like there's very little you can do if you don't know anything about X and Y. And that's almost true, but let's do a little thought experiment. So, to win the game, you don't have to know the values X and Y. For example, imagine for a second we know some value Z, and X is less than Z is less than Y. So we know this, we don't know X and Y. But then the game becomes easy. Because what's my strategy? I open the box, I see some money inside. If the amount that I see inside is less than Z, then I know it's not the big box, right? It's the one with X dollars in it. On the other hand, so I should switch. And if the amount I see inside is more than Z, then I know I should keep that box because the other box contains less than Z. So I don't actually need to know the values of X and Y it would be enough if I knew a z in between x and y. All right. But we don't know that. So instead, we will pick a random z in 0.5, 1.5, 2.5, 3.5, all the way up to 99.5. So I would really like to know a z that falls in between x and y. So instead, but I don't know that because I don't know x and y, but instead I'll pick a random z, and I'll pick from this set so that I know it's not equal to x and it's not equal to y, because x and y are integers. And no matter what values of x and y I take, I know at least one of these things will fall in between them, right? Even if x is 1 and y is 2, then 1.5 is in between those two things. And there's nothing outside this range that I should pick, because smaller than 0 is useless and bigger than 100 is also useless. All right, so that's the game. You pick a random z, look in a box, and see $. If z is less than, let's say if z is bigger than a, then switch boxes. Otherwise, keep the box with $. Okay. What's the probability of winning? Okay. Now, if we want to make a question about probability, we should then carefully figure out, okay, what is the sample space? What's the probability distribution? So let's write down carefully what we have here. So really only two things happen, right? So if I wanted to find the sort of things that can happen in this experiment, one of them is I look in the box and I see $8 in that box. And the other is I pick a value of z. Okay? So A is either x or y, and z is in this set 0.5, 1.5, up to 99.5. Okay? Now I pick, or the boxes have been shuffled, or I toss a coin to decide which is the one that I open. So it's equally likely that A is I'm going to see X in it, or that I'm going to see Y in the box. And the value Z I chose is also equally likely to be any of these things. So what I have here is a uniform probability space. Okay? So that says for any thing in S, the probability of that thing is equal to 1 over the size of S. And what is the size of S? Well, how many choices are there for A? There's 2. And how many choices are there for Z? There's 100. So size of S is 200. So there are 200 different ways that this experiment can unfold. And I'm interested in the ways in which I win, this W. Okay. So what does this set W look like? Well, it's easier to split it up a little bit based on the contents of this box that I open. So it could be, so I'll write this. I win if I open the box that contains X and I win, or if I open the box that contains Y and I win. So this WX is the outcomes that look like this. There's an X and a Z, and when am I going to win? Well, I'm going to win if Z is bigger than X, because if Z is bigger than X, I'll say I don't want to keep this box, I'll take the other one instead. When is Z bigger than X? Z is bigger than X when it's X plus a half, or it's X plus 1 plus a half, or it's X plus 2 plus a half, all the way up to 99.5. If I open the box that contains X and I happen to pick a value Z that's bigger than X, then I'm going to win, because I'm going to just get rid of that box and take the other one, which is the correct box. All right, what's the size of WX? I'll forgive you if you don't see this immediately, but it's actually 100 minus X. And if you want to see that, just think if X is 99, then the only way that I can win is if I pick 99.5 as my Z value. All the other Z values are smaller. So that means the only way that, there's only one way to win if X is 99. On the other hand, if X is 98, then if I pick 98.5 or 99.5, I win. So there's two ways to win. So that means the number of ways to win, I mean, it fits for those two values of X, and it actually fits for every value of X. It's just 100 minus X. Okay? So that's one side of it. And the other side is, well, if I happen to open the box that contains Y, how do I win in that case? Well, in that case, I win if the value of Z is smaller than Y. So if I picked Z to be 0.5 or 1.5 or 2.5, as long as it's smaller than Y, so the largest one that I could pick is Y minus a half. Any larger values of Z I'm going to lose because I'm going to switch boxes. So what's the size of WY? Well, you can think of it as I start counting at at 0, and I end at Y minus 1. So size of WY is just Y. Okay. So want to know the size of the set W. W is the union of WX and WY. These two sets are disjoint, right? Because one of the sets has X. All the elements have X in the first coordinate, and the other set, all the elements have Y as the first coordinate. So these are two disjoint sets, which means that the sum rule tells us that that's the size of WX plus the size of WY. And we know what that is. It's 100 minus X plus Y, or if you like, it's 100 plus Y minus X. Okay. This is, out of all the 200 ways that the experiment can unfold, this counts the number of ways in which it unfolds, and I pick the correct box. So the probability of W is just the size of W over the size of the sample space. That comes from here because it's a uniform sample space. And, or uniform probability space. And so size of W is 100 plus Y minus X. Size of S, we decided, is 200. 100 over 200 is 1/2. So I have 1/2. Yeah.
Good question. Where does the WX union WY come from?
It's just me trying to figure out how big this set W is.
That explains it.
And it's easy to break it up. I mean, break it up into two cases. Either I open the box that contains X, or I open the box that contains.
That explains. Is W the number of chances to win?
I mean, this is the WX is the number of chances to win if I open the box that in which I open the box that contains
W
X.
means win, right?
Yeah. All right. So I have 1/2 plus Y minus X over 200. Can you tell me anything about Y minus X? So back to the definitions. X is less than Y, and X and Y are integers. So Y minus X is at least 1. So that is bigger than or equal to 1/2 plus 1 over 200. That's 0.505. That's true for any choice of X and Y. So no matter what X and Y I picked here, if you play this strategy, you have a better than 50% chance of guessing the correct box. And that I find is a really surprising result, because on the face of it, it looked like you couldn't do anything to do better than guessing randomly. But in fact, you can. And actually, once you analyze this, you realize actually this is a really good game for you, because take a step back from this last inequality. What you see is it's 1/2 plus Y minus X over 200. So as the difference in the amount of money in the two boxes grows, you have more and more chances of winning with this strategy. So in particular, if Y is 100 and X is 0, then for sure you win. Right? Then this is 100 minus 0, so for sure you get the correct one. And on the other hand, if X and Y, if the difference is only $1, I mean, who really cares whether you win or not? Plus or minus $1 is no big deal. But you do start to care if the difference becomes $50 or, I mean, it matters like if X is 1 and Y is 50, I'd really rather have the $50 than the $1. So that's your second surprising result for the day that maybe you haven't seen before. All right, so that's a good place to leave it today.